Hello and welcome to our group presentation. Our final project was a maze solver control program that used both the line following sensors and sonar sensing to complete a maze. Our group is comprised of Neel Choudhary and Nicole Danuwidjaja. So let's get started. First off, we want to talk about our project proposal. Our goal for this project was to write a control program for our robot, the mBot, to successfully solve a maze at a given point using both line following and sonar sensing. Some of the key objectives here were to have the robot move autonomously without any human input using line following techniques to navigate through the maze. In addition, we also wanted to have it identify surroundings using the sonar sensor in order to find the next optimal path. And lastly, we used the sonar sensor to help supplement the robot to identify the correct goal. So overall, our project proposal was to put a twist on a maze solver and use additional sensors to be able to complete this task. Our project breakdown was comprised of 5 key steps. First was to construct the physical robot itself, which we used from the recommended kit. And then we also wanted to establish computer and mBot serial communication, which was crucial to be able to actually write control program code. Then we wanted to connect the firmware and write functional code so that we can port the code to Arduino, so then the Arduino motherboard was able to gain information. Then we wanted to connect firmware and write functional code so then the Arduino motherboard would be able to function properly. And the next part of this was to actually build the maze to test this out. So we wanted to determine a maze layout and build a physical course so then we can actually use the physical robot. And lastly is to translate all of this into a gazebo simulation. So we wanted to create models to replicate this maze. So after all these 5 steps, here's what we've presented to you today.
We decided to go with the mBot Ranger from mBot as recommended by the course instructors. The robot came with an ultrasonic sensor, a line following sensor, 2 motors for movement, and of course, the Arduino motherboard. Since we had 2 robots, we decided to combine parts from both robots and attached an additional line sensor onto our main robot. As you can see in this image, we added an additional line sensor on the right side of the robot. This allowed us to more easily detect intersections in our maze. In order to construct our maze, we decided to construct it using large drawing sketch paper and black duct tape. We went with a 1.88-inch width to represent the lines, as this covered the sensor's range. This picture shows how the mBot line following sensor works. The sensor returns numerical values based on the infrared signals reflected on the black duct tape. We use these readings to determine whether the robot should either continue to move forward or whether it should correct itself by moving slightly left or right to go back onto the black line, the black duct tape. As you can
We also wanted to highlight some progress throughout this whole journey. So we first started with testing out a single piece of drawing paper, and then we tested if the robot could navigate successfully by identifying the sensor with the line following sensor. And then we mapped a simple course, which was just a loop where it would only have one way to go, and it would just infinitely circle the environment until it ran out of battery. So from this, we gathered that we had a good starting point for our project, and then the next task was to be able to properly identify intersections as well as optimal paths for the robot. So for our code base, we structured it so then we had 5 key parts. We had the brain, which contained the libraries for actually uploading the code through the existing firmware. And then we had the robot classes and the control program itself for both virtual and physical bots. We started off with Professor Tuck's implementation of the basic robot class and porting that to either the Gazebo robot or the physical robot. And then we also expanded this to have additional models and plugins for our Gazebo robot. So we had Gazebo model files for the virtual maze, and we also had shared Gazebo libraries from the help of some other teams, such as Nolan's. And through this, we were able to successfully create, which we will show you on later, in a virtual maze. Then we also had additional sketches that we used to upload to the Arduino firmware, which enabled us to use the mAriga firmware provided, as well as write and port our own control program.
As you can see in the physical maze that we constructed, we constructed it in an empty room in order to avoid interference from our sonar sensor, and we used a large green water bottle to signify the end of our maze.
Based off the location of the green water bottle, we are able to detect, using the robot's ultrasonic sensors, detect the optimal path for it to take. So in this route, the robot would be able to avoid the cycles within the paths and find the green bottle successfully. Now for our Gazebo simulation, we wanted to use the same map so then we can see if the performance of the robot is equivalent for virtual and physical. And we were able to successfully create this through our project structure that we enlisted. And we created a model that replicated the physical mBot. So our Gazebo model also had 2 line sensors, which were key to the overall performance of the bot's line following, and we also had the ultrasonic sonar sensor. So for our virtual maze, you can see it is pretty much the same, and we wanted to also replicate the sonar sensing with the object, so we created a cylinder goal object.
In order to communicate between our control program and the Arduino, we use serial communication based off Nolan's starter code. However, we modified how the firmware sends sensor data by sending all the important data we needed in one string, which is then parsed by the control program. The main sensors we used were the 2 line sensors, the sonar sensor, and the Z pose. Unfortunately, when it came time to actually test it on the maze we created, we realized we could not have a wired connection because we only have a PC and not a laptop. So instead, we ended up rewriting our firmware to include a control program logic. We had to make some changes to reduce memory usage given the limitations of the Arduino board. But we were able to get it to work, so in the end, the serial communication was not necessary since all our logic was contained in our firmware program. This is also why in our video, the robot runs on its own without any cable connected to it. Our control program's goal was to solve the maze. We used the line following sensors to keep us from deviating from the black line and to detect when we were at an intersection. When the robot is at an intersection, it will spin in a circle to identify all the possible paths it can take. It also records sonar data to detect where the goal is at. It then chooses the path with the smallest angle to the goal. The robot knows it's at the goal when the sonar sensor detects an object within less than 10 centimeters from the robot.
Throughout the project, we faced numerous interesting components that we created. First off being our control program working across multiple different subsystems for the mBot. So we found that it was very interesting to see that we were able to experiment with the different components, such as the LED lights, the Bluetooth connectivity, and also the sonar sensor and the line following sensor. And the mBot actually enabled us to really experiment with what we wanted to do with this project. So at the end, we decided on focusing on the line following and the sonar sensor because we were able to construct and work out our experiment for a maze successfully. Another interesting component was that we were able to compress the firmware, as Neel mentioned earlier, and this enabled us to load the entire control program onto the Arduino, which had a very limited memory space. And lastly, we were also able to mod the mBot, which was something we didn't anticipate on doing when we started, but ended up seeing that this was a very interesting and intriguing way to solve a common problem for a maze solver. So by using multiple line following sensors, we're able to better read data for the lines and also gather data through sensors rather than relying on a specific algorithm. Which brings us to our next point. Expected challenges. When we first started this, the huge elephant in the room was what kind of algorithm would we implement? And we were thinking of using some of the techniques from the homeworks or using backtracking. And we determined that we wanted to really play around with the physical hardware. So we wanted to have a huge reign of control over what kind of data we can get and how we can manipulate it. So we wanted to use additional sensor data to be able to gain the position / best path for the robot. So our next thing was to be able to port code for both the physical and digital robot, which we largely relied on from Professor Tuck's code. But we realized that tracking expected behaviors, both digitally and physically, was going to be a challenge, and this is what we highly anticipated it to be. Since we were largely uncomfortable with using the physical hardware, it was a challenge at first to set up everything, but after we got over that initial hurdle, it was interesting to learn about how to create and write code for a physical robot. Now, for some unexpected challenges, we didn't realize that it would be as difficult as we experienced it to be to set up the firmware, but we also had difficulties just with testing code on the mBot due to some of its firmware limitations, such as short battery life, and we actually went through over 80 batteries just to test our program because of the very short life that the mBot was capable of having. And we also had difficulties with establishing communication, but all 4 of these hurdles were largely because of the inexperience that we had with the physical robots, and largely it became a huge learning experience as we overcame those challenges. So now for our physical demo. As you can see, we turned on the robot and it autonomously moved on its own. And as we described earlier, the robot will identify an intersection and signify with the LEDs what it's currently doing. So right now it's spinning, and then it will, based off the location of the goal, identify what direction to go into and see where is its next best path. So here it's going to be taking a right instead of going backwards because that angle is much closer than the going backwards angle would be. So as we continue filming this, you'll see that the robot is largely consistent in its behavior. Each intersection, it will circle around and view all possible paths, and then it will use the ultrasonic sensor to see where the goal is and situate itself towards that. Using this reasoning, this is how we have largely written our control program to be both robust and accurate, and the robot ends up correctly finding the path and stopping when it reaches the goal. And the LED lights will turn green. So thank you for listening to our presentation, and have a great day.